Swayam Prabha. Digital India. Educated India.
In the last week, we looked at how network virtualization and overlay networks helped overcome the internet impasse and enabled the researchers to continue experimentations over the virtual testbeds. This week, we will continue and see what other developments happened towards network deossification and to facilitate better control over the network. Our primary focus for this week would be software-defined networking, or more popularly known as SDN in short. And this SDN, when we say, it refers to a networking architecture that virtualizes the network where the network control functions are decoupled from the network forwarding functions and also enable the network control to be made directly programmable. We will look at these two aspects in detail, and before that, let's try to see what actually happened or what were the points and reasonings that were made for this SDN. And I often point to this famous quote by John Day. And this, seemingly a bold but courteously a very true statement, wherein he pointed out that we often believe the things to be the paragon of engineering at a given point rather than understanding that they are the snapshots of our understanding at that specific point in time, which is also true when we look at internet as a marvel of engineering, right? And this often leads to how we try to advocate about the merits and demerits likewise. But often what we end up doing is profess on specific aspects than re-inquiring and looking at the other aspects. And this is what John Day pointed it out rightly and towards what happened with the internet. Nonetheless, we do need to understand that learning is a continuous process and progressive evolution is a natural phase only when we continue to reason and inquire about everything. So, let us begin our journey on SDN and try to briefly look at one of the most cited papers. And this paper was actually almost a decade ago, published a decade ago, and that clearly illustrates what things happened in breaking out this SDN. And in fact, this paper traces the intellectual history of programmable networks, including the very early efforts of active networking and the efforts to separate the control and data planes, including the works on OpenFlow and network operating system. So I'll try to summarize the key aspects that are discussed in this work in a very brief manner. So we can think of this paper as three specific aspects. First is the active networking, which in fact was the first of its kind to introduce the notion of programmable networks. So let us look at active networking and then jump in to the other two aspects of separation of control and data planes and the emergence of network operating system. So the first, as you see, the active networks were the first of the attempts that were made to make the networks programmable. And in this, even the advancements of the processors or the processor technologies, wherein the significant reduction in the computation costs actually propelled for the research on active networks. In essence, what active networking represented is a radical approach to network control by envisioning a programming interface or a networking APIs that are defined and exposed. For example, the processing, the storage, the packet queues, for each of the functions that happen within a network, the APIs be exposed on each of the individual network nodes and be supported in terms of a custom functionality that can be modified by the incoming packets. Or a subset of the packets that traverse through the networks can modify these functionalities within the network. So now you cannot think as packets as just the passive data that is being transmitted from one end of the device to the other, but also the data contains the active part which can manipulate and process and change the way the network behaved for processing of these packets. And that's what really led to active networking. In a very nutshell definition, it's like a communication pattern that allows the packets flowing through a telecommunications network to dynamically modify the operations of the network itself. And to understand it more prominently, let us try to see what actually active networking offers. It's basically a networking paradigm where the bits that are carried are in more general constitute the compute and data. Just as what we do a program contains the set of instructions that enable to operate on the data and manipulate the data. Likewise, now the packets that are transmitted contain the code which can be operated over the networking elements themselves to instruct or to modify the existing actions. So if we see this figure here, as a transmitter, you want the data X to be transmitted, which constitutes of both the data that you eventually want the receiver to receive, say a Y, or not necessarily the same data as what you transmit, but a function of that data that will eventually result in the receiver receiving the data Y on the other side. And to make this happen, you also add the code that would operate on this particular data X within the network, and where this manipulation or the function when it is run would actually translate this X of data into Y, which the receiver needs to receive. And at the same time, if there is a code that needs to be operated within a medium and make sure that some properties of the medium be changed from the initial state of medium to medium prime, then this X code would facilitate to make this channel operate and build. Let us think of a very simple and a naive example of how the NATs operate. Right? And what happens when we try to do the NAT? You need to have the private and public IP matchings that are being set. Now, this allows anyone from inside the network to communicate outside to a public IP. But what about the other way? We know that we cannot reach back to a private IP unless we know that there is a mapping that is being set at a NAT device pre-set. That is a rule that exists to say that what would be the public IP and port to which it can translate back to the private IP and private port. And this is not possible without the usage of the stun or turn aspects, where you have to write the traversal mechanisms and say that you can reach the device that is within a private network. Now, if we are able to embed the code and data and ensure that as the packet traverses, it can set up this functionality of mapping within a NAT device so that now you are able to access and reach the other side of the private network, our job is done. So that way, the active channel is actually building the rules or mappings as you go. And this is exactly in a sense of what active networking tried to offer, but for different portions. Like when you want to manage or when there is a change that you need to do on the network routers or switches, you can, instead of going to program, get to the device and change, you could as well send the data that could make the updates, that could even reflect the status back to the user and help user do the necessary actions. And this is where the active networking started, and thus offered a major change in the networking paradigm. Nonetheless, this was not as much successful because of the complexities that had in terms of the deployment, but it essentially paved the way of how we can think of networks to be active. And now, if we look at it in another sense, the networks in the earlier week, last week, when we discussed about the end-to-end arguments, we said the networks will be bare minimal and dumb pipes that would just transmit the data. And now we are talking completely contradictory to it, where we are emphasizing that networks can even manipulate the data and act on the data. It is as well as empowering the network to generate data on its own and transmit the data to the receiver the way the receiver would want to get, rather than what the transmitter would want to send. So These conflicting aspects also brought in, but for the good in terms of how we can think of networks as no more as a passive elements, but as active elements that can also help aid for better running, better management, better control over the network. And there were several of the intellectual contributions that were made by this active networks. One, to say that they enabled the programmable functions in the network. And what we see with middle boxes is exactly the same, where you have the middle boxes that manipulate on the data, like NAT, what we discussed. It actually translates the packets, headers, right? IP header and L4 headers, the port and IP mappings are changed. And likewise with the firewalls and load balancers. So these are all as a programmable functions which are now being considered part of networks. And this notion of programmable networks, in a way, lowers the barrier for network innovation so that we can think of adding innovations right into the network. In fact, data plane programmability is again coming to the forefront in what we are going to learn as network function virtualization. And the most second aspect with this active networks is the network virtualization, wherein it provides the ability to demultiplex the software programs based on the packet headers. And what that means is we could embed the programs onto the packet data, and based on the type of packet data, different programs can be executed within the network and manipulate on the traffic before we transmit and forward. In essence, is a kind of a virtualization that a network provides over the functionalities that it can build. So the construct of this active networks was based on two kinds of programming models. One as the capsule model, where the code that needs to be run is carried in band within the data packets, as we saw in this diagram here, where a packet would carry the X code, and X code is the one that is being operated on the network medium and transition its state from medium to medium prime. And this was in fact the most powerful of the model that became very popular, while the other was a programmable switch or a router module, where the switches or routers wherein we want to run the code could be established in an out-of-band fashion, and the functionality that you would achieve either way is the same, but not necessarily that the data, the code is carried in band within the packets, but these can be specific sets of controls that you want to build. And this is again what we see when we want to manage specific devices. This out-of-band model really suits it. And this, in a way, active networks, although it didn't succeed over time, but it paved the way for how we can see the networks to be programmed. And the second of the tiers is the separation of control and data planes, and which is what we actively refer to or know as the software-defined networking. In fact, this was the initiation journey for SDN, wherein the disaggregation of the hardware with respect to the software that would manage and control started with the enumeration of open interfaces. And in here, let us look at some of the key works that set the path for the separation of control and data planes. The first of the work is the Tempest that was put forth late 90s. And here, the authors discussed about how to allow the third party to access the network without jeopardizing the network integrity. Or in essence, how as a network owner, like a campus or enterprise network, how I could accommodate legacy networking solutions and then also have a programmable environment defined for my custom networks. That was the core of saying how you would want to separate out the control over the network and what, in essence, the data part of the network needs to do. And this, in fact, led to the setup of an IETF working group called the Forces, or Forwarding and Control Element Separation. And this work, in fact, this IETF working group led to a series of RFCs charting out the key requirements, the framework for Forces, and the protocol specifications, and many things started to emerge in the plane of control and data separation. In fact, It also led to a protocol as a means to separate the forwarding and control elements from the transport. And if you look at TCP, we have so many of the flags that try to control the way the data would move and needs to be handled. But now, if you think of transport protocol, which is specifically meant on one side to carry the data, the other side to carry the signals, and you want to separate these out. And in fact, this led to what we call as the SCTP, or a Stream Control Transmission Protocol, which is widely used in many of the real-time streaming applications and various of the live calls, etc. And this has played a major role in setting up of many of the aspects when we look at the framework for the control and data plane separation. Next up, there were RCP, soft router, and PCE 4D works. Let's just try to look at what this PCE and 4D really meant. PCE stands for Path Computation Elements, which brought the notion of having a dedicated server which could basically decouple the computation of the paths or the network paths from the routers and do the computation of the paths on behalf of the network routers. So we all know that when the routers compute the path, they all do it independently. Now think of one server that can do this computation for many of these routers. And what this means is this path computation offload that happens to a dedicated server. It could be a general purpose machine, it could be one specific router itself. And then this, in a way, ensures that you are now able to virtualize the way the routing is done for a specific domain. And that was the initial separation of how the functionality of routing could be even thought as a separate entity which can be decoupled from the routers themselves. And this centralization of path computation, in fact, enables the operators to customize and control the routing policies and algorithms that you would want to run from a single location. That is more important because now if you want to change anything, you are just to go and update at one place rather than going and updating at several of the routers that are spread in the network. And that's the flexibility this PCE started to provide. And this work, in fact, influenced and led to what we see as a 4D project that started, which was in fact the clean slate architecture for network control and management. And this work was guided by three principles. First is the network level objectives. That is, when you try to run a network which needs to have robust data characteristics, that is in terms of satisfying the performance objectives, or the reliability objectives, or the policies that you want to ensure to be met when you want the network to transmit specific packets or flows of packets, you want to guarantee those network level objectives. And to do that, assurance of meeting the network level objectives, what you really need is a network-wide view which is more timely, accurate, and is able to provide the precise characteristics of what's happening at each of the links or the topology of the network, which can eventually be able to help achieve the network level objectives of providing a robust network. For example, if there is a link failure, you want to have that view then and there rather than waiting for the routers to converge and decide what would be the alternative path. You would want to know the instance the link fails and reroute or change the path of packets so that you are able to adapt pretty quickly and in real time. And thus you are able to meet the network level objectives. Right? So this means that there is a need to have the network-wide views in a timely and accurate fashion. And in order to have this timely and accurate updates over the entire network, it would also call for having a direct control. That is, once I know that, okay, there is a failure of a link, I should have the control at each of the elements directly to say what would be the best alternate path which can be taken immediately rather than waiting for the routing algorithms to converge and then set up the alternate paths. So the decision logic should be provided to the network operators with a direct interface so that they can configure the network elements much more precisely in real time. And these were the key guiding principles of the 4D project. And what this 4D really meant is to look at the network or view the network elements in four distinct layers of what we call the Ds. And the groundmost at the lowest layer is the data element, where it is confined towards processing of the packets alone, wherein it is just as the dump pipe that would take the data, and based on the rules that are being set, it would forward the data. So forwarding is a key aspect, and the rules that are necessary for forwarding have to be configurable in real time. And the second of the layer that is built above is the discovery layer, and this discovery layer is crucial in providing the topology characteristics at a given time, and also the traffic measurements in terms of which devices have the link bandwidths that are getting overutilized, that are getting underutilized, or what is the queue occupancy at each of the devices, what is the current communication topology looks like, which links are up, which links are down, kind of information in real time. So that's being managed by the second of the D, that is the discovery layer. And once you discover the aspects in a network, you would want to quickly disseminate this information so that the decisions can be taken in a real time. So the third of the layer is the dissemination plane, and this dissemination plane enables the information collected by the discovery and the local information to be sent out to the network operators for installing the packet processing rules that are necessary or changes that need to be made in real time. And this dissemination layer, once it's done, it is also important to have a decision plane. And this decision plane can be logically a centralized place wherein the decision for the entire network, not the distinct elements, but for all the elements in a network, can be taken at one place. So this consists of a logically centralized controllers to think of that can convert the network level objectives that you have based on the information that get disseminated to them from different entities in the network. So this is like a point where I can have a software or a program that can run, adapt, and tune the network characteristics to make and meet the network level objectives of having a robust network. And in fact, this work paved the way further for how we think of today's software-defined networks. And the third of the tier is, in fact, the evolution of the open flow and network operating systems. And in here, you can see the lot of works that started with ethane, leading to open flow, Onyx, ONOS, Nox, and various other works have come in the recent years. And the most fundamental work in this is the ethane, which published, I think, around 2007, and it in fact was influenced by the 4D project from IIT. And this ethane brings the vision to life, wherein we want to concretize several important aspects like how to boot up, what is the registration, policy setup, deployment aspects of the networking devices like routers and switches. And this ethane work has been seminal in many aspects, wherein it paved the way to move the control plane out of the switching elements, and also towards building a centralized controller wherein one element can take the decisions on behalf of the other switches and routers in a network. And ethane's approach to define the APIs or mechanisms to make this communication from these switching and router elements to one of the centralized entity as the network APIs led or influenced towards the creation of OpenFlow. And OpenFlow started around 2008. And eventually this ethane and OpenFlow led to a startup called Nisira, which was later acquired by VMware, and what we now know as the OpenFlow's outbound APIs and the SDN with a control plane has become a common norm. And this in nutshell is the eventual roadmap of how the SDN, what we see today, started. And much of the works are there to follow. And in fact, over the last decade, there have been more than thousands of publications in the area of software defined networks alone.